Hello and welcome. Today, we're diving into a really cool algorithm that, believe it or not, powers some of the most essential tools you probably use every single day. We are talking about the longest common subsequence, or LCS for short.
So, have you ever been working on some code, you run git diff, and it just magically knows exactly which lines you added or deleted? It feels like magic, right? Well, it's not. The secret sauce behind that is the algorithm we're talking about today. So, in this explainer, we're going to break down what a longest common subsequence even is, figure out how to solve it using a simple grid, and then we'll look at all the surprising places it shows up in the real world.
All right, first things first. Before we can go finding the shared pattern, we need to get super clear on what we're actually looking for.
Okay, so a subsequence is a pretty simple idea, but it's really powerful. Imagine you've got a word. You can make a subsequence just by deleting a few letters. But, and this is the most important part, you absolutely cannot change the order of the letters that you leave behind.
Now, this is a super common point of confusion, so let's clear it up right now. For the string ABCDE, AC is a perfect subsequence. We just got rid of B and D. But something like BCD is a substring, because those letters are all neighbors, all clumped together in the original. The LCS algorithm doesn't care if the letters are neighbors, it only cares that they appear in the same order.
I absolutely love this analogy. Finding the longest common subsequence is kind of like reading two different books and pulling out the main plot points they have in common. The stories might have extra characters or side plots, but that core narrative thread, that's your LCS.
So, how in the world do we find this shared thread? Well, the classic way to do it is with a technique called dynamic programming, and it all comes together in a really simple grid. Seriously, this is where it's all gonna click.
Okay, don't let the math here scare you. It looks a little intense, but think of this as just the rulebook for a little game we're gonna play. It tells us exactly how to fill in each square on our grid based on the squares around it.
Let's just boil that down into 3 dead simple steps. For any square in our grid, you first ask, do the characters for this row and column match? If they do, great. You look at the number in the square diagonally up and to the left and you add 1. If they don't match, no big deal. You just look at the number directly above you and the number directly to your left, and you just take whichever one is bigger. That is literally it.
And voila! This is what you get when you apply those rules to the strings AGTAB and GXTXAY. You can see how the numbers build on each other. And the grand prize, the final answer for the length of the LCS, is always waiting for us right there in the bottom right corner. In this case, it's 4.
But wait, that's just the length. How do we get the actual sequence? Well, we just work backward. We start from that final number. If the characters for that square matched, we know it's part of our sequence, so we write it down and move diagonally. If they didn't match, we just move toward the bigger of our two neighbors, either up or left. You just trace that path all the way back to the beginning, and you've got your answer, GTAB.
Okay, that grid is a fantastic way to wrap your head around it. Now let's talk about what it looks like to turn this logic into actual code and, how it performs. The time complexity is what we call theta of n times m, where n and m are just the lengths of our two strings. And why is that? Well, it's pretty simple actually. To find the answer, our algorithm has to visit every single cell in that n by m grid. It can't skip any. So the time it takes is directly proportional to the size of the grid.
So, when you're actually coding this up, the most important thing to remember is that if you need to get that sequence back, you have to store the entire grid in memory. Then you just implement that backtracking logic we just walked through. And of course, you gotta handle the simple stuff, like what happens if one of the strings is empty.
Now, storing that whole grid is fine for short strings, but if you're comparing, say, 2 massive files, that O of n memory usage can be a killer. Thankfully, some very clever people figured out ways to be much smarter about space.
This slide lays out the trade-offs beautifully. The basic approach is simple, but it's a memory hog. Now, if you only need the length and not the sequence itself, you can use a trick called a rolling array and get your space usage way down. And if you need the best of both worlds, the sequence and low memory, there's Hirschberg's algorithm. It's more complex for sure, but it gets the job done in linear space, which is incredible. That rolling array trick is just genius. You realize you only ever need the previous row to calculate the current row. So why keep the whole table? You just keep 2 rows and swap between them. Hirschberg's algorithm is more of a divide and conquer approach. It's a bit of a mind bender, but it lets you rebuild the sequence without ever storing that giant grid.
So now that we know how it works, and even how to optimize it,
Let's zoom back out and see where this awesome algorithm actually shows up in the world.
And here we are, full circle, back to our first question. Version control systems like Git use LCS to generate those diff outputs, but it's also a cornerstone of bioinformatics for aligning DNA and protein sequences, and it's used in software that checks documents for plagiarism. It's everywhere.
What's really fascinating is the history. A whole bunch of these foundational algorithms for comparing sequences, including LCS, just exploded onto the scene in a few short years in the early 1970s. It was this perfect storm of new challenges coming out of biology and computer science at the same time. This chart is the perfect summary for any engineer thinking about using this. The main takeaway is super clear. Your time cost is pretty much locked in at n times m. But you have a ton of control over your memory cost, and the right choice just depends on whether you need the sequence itself or only its length. So if you remember just 3 things from all this, make it these. Number 1, the whole solution is built on that simple set of rules for filling out the grid. Number 2, the time complexity is always going to be tied to the size of that grid. And number 3, you can get really clever and dramatically reduce the space you need. All right, I want to leave you with one final brain teaser. We have totally mastered finding the longest pattern the 2 strings share. So what if we flip the problem on its head? How would you find the shortest possible string that contains both of our original strings as subsequences?
It turns out the answer is directly connected to everything we just learned. The length of this shortest common supersequence is just the lengths of your 2 strings added together minus the length of their longest common subsequence. And why does that work? Because that shared part, the LCS, is the overlap. You don't need to include it twice. Pretty neat, right?
And that's a wrap on the longest common subsequence. Thanks so much for diving in with us.